Hi everyone, so in this video series we are going to walk through designing data-intensive applications, which is a highly influential and popular book on designing scalable systems. So in each video we will look at one chapter from the book and I will describe the key takeaways from the book. The book delves much deeper into these topics, but we will highlight the main ideas so that it helps you to grasp the material. And if you decide to read the book, it's much easier for you to absorb what is being discussed in the book. So today we will be looking at chapter 1. So let's get started. So chapter 1 is about reliable, scalable, and maintainable systems. So this book is about data-intensive applications instead of compute-intensive applications. In data-intensive applications, the bottleneck is either the amount of data or the complexity of the data or the speed at which the data is changing. And so we will look at the different aspects of data-intensive applications. But first, let's look at some of the building blocks that are commonly used in data-intensive applications. So you might be familiar with databases. So they are used to store data so that the database or another application can find that data again later. Caches, which basically remembers the result of an expensive operation, and this helps us to read the result much more faster. Search indexes, which allows users to search data by keyword or by filtering the data in many ways. Stream processing, which sends messages to another process to be handled asynchronously. And the last one is page processing, so periodically crunching a large amount of accumulated data. So these are some of the building blocks, and the purpose of this book is not to help you to implement one of these building blocks, but to understand some of the trade-offs and design details of some of these building blocks so that you can, given your application, you can reason about which database to use or which sort of caching mechanism to use or what kind of page processing framework should you use. So that's the main sort of idea of the book. In this chapter, we will be looking at the non-functional requirements of these systems. So the functional requirements are the ones which defines the functionality of the system. For example, what the system should be doing or providing to the end user. Whereas non-functional requirements have many sort of aspects, but the three common ones that are discussed in this book are reliability, scalability, and maintainability. So we will look into each one of these in turn. So what is reliability? A system is reliable when it can continue to work correctly, even when things go wrong. So working correctly could be defined as it provides the expected service to the end user, and things going wrong could be defined as the faults that occur. So here, the book highlights that faults are different from system failures. Faults are when parts of the system are not functioning, whereas system failure is when the whole system is not functioning. So what kind of faults are there? There are hardware faults, software errors or faults, and human faults. So let's look at each one of them in turn. So hardware faults typically are random and uncorrelated. So here one machine dies, there another machine dies, and they are usually sort of uncorrelated. And this kind of failure is pretty common because hard disks and other hardware have some mean time to failure. For example, a typical hard drive would have 10 to 50 years of mean time to failure. When you have thousands and thousands of hard drives, you you are bound to see some failures of those hard drives. So how do you avoid or become tolerant to hardware faults? A reliable system should be using redundancy to be fault tolerant, and also use software that can withstand the failure of a single machine or a single hard drive. So that's how do you combat hardware faults. The next sort of faults are software errors. So they are much more systematic and correlated across nodes. So if you have a software bug, it will infect or sort of affect all of your system. And that's why software bugs are the cause of many more system failures than hardware faults. One of the reasons software bugs are so difficult to handle is because they often lie dormant for a very long time until they are triggered by an unusual set of circumstances. So the example, a concrete example of this would be the leap second on June 30th, 2012, which caused the Linux kernel to hang. So these kind of problems can sort of make all of the machines in a system to a halt and cause a failure. So the book offers many different remedies for dealing with software errors, but the bottom line is being able to allow processes to crash and restart. Being tolerant of these errors is the way to go. And the final set of errors discussed are the human errors. So configuration errors by operators is a major cause of outages, according to some studies. So in order to combat human errors, your system should be able to allow a quick and easy recovery from human errors, so that its impact could be minimized. So that's all about reliable systems. Let's talk about the other aspect, scalability. So a system's ability to cope with increased load. Now, you would think, what is load? So load is very specific to the kind of application you are building. So it could be requests per second to a web server. It could be the ratio of reads to writes in a database. It could be the number of simultaneously active users in a chat, or it could be the hit rate on a cache. So it's really dependent on what is the bottleneck in your system. So you can't pick the easier number. You have to analyze your system much more deeply to find out what are the bottlenecks, and that's your load parameter. So let's take a really concrete example of the Twitter. So Twitter has two main sort of functionalities that we are discussing here. One is posting the tweets, and it according to some reports from 2012 discussed in the book, the Twitter load is about 5,000 requests per second for writing or posting the tweets on average, and 12K per second at peak load. And the home timeline read requests, where a user requests to sort of see their timeline, they are about 300,000 requests per second. So posting the tweet, the 5,000 requests per second is not the problem for Twitter. The problem is the fan out. And the fan out is when you send a tweet or post a tweet, it has to go to all your followers. And each user has many followers, and each user follows many users. So this causes a lot more queries to the databases. So there are two approaches to handle posting the tweets and retrieving timelines. So we will look into both of them. So approach one is to simply, when someone tweets a new tweet, insert it into a global collection of tweets. So you have a tweets table. Whenever someone do a tweet, insert it into the tweets table. And then when someone requests a timeline, you just find all the tweets of everyone the user is following and combine it into a home timeline. This SQL query basically combines the users table, the follows table, which contains the follower and followee IDs, and retrieves all the tweets from users where the user is a follower of the users who is tweeting. So this works fine until there are too many users, and so then the 300K timeline reads up to 300K. It might be suitable, but imagine there are 3 million users, and then in that case, if 300 million users are active at a time, then that's a lot of timeline read queries. So when Twitter used approach 1, the system struggled to keep up with the load of home timeline queries because the user base was increasing, and so the timeline read requests were also increasing. So they switched to approach 2, which is intuitive, described here in the diagram. So when a user posts a request, it is put into a queue, and then each follower of this user gets the tweet returned to their cache. So each user has a cache for their timeline, and their timeline is computed ahead of time before they log in. So when this user do a post, it is being sent to all of their followers. So follower 1, follower 2, follower 3. And so if you have, say, 5K tweets per second, and if each person has, let's say 100 followers, then there could be 500K writes to each of the follower, or 500K writes in total. So the good thing about this architecture is that the rate of posting tweets is much lower than the rate of home timeline reads. So we solve one of the problem of having to have read requests that are in the order of millions of read requests per second. But the problem with this is if this user has, let's say, 30 million followers, if they are an influencer, then every time they do a tweet, that tweet has to be sent or written to each of their followers' timelines. And that one tweet would cost 30 million writes. So that's the trade-off between whether you want to support a whole lot of users, which will be supported by this approach, or whether you want to support users who have very, very large number of followers, which will be handled by approach 1. So this brings us to the load example. So in the Twitter example, the distribution of followers per user is a key load parameter for discussing scalability, since it determines the fan-out load. So if you double the number of followers, how does your system deal with that? Can it keep up the performance? And so this brings the question of how do we discussed load, but how do you measure performance? So performance could be, when you are measuring performance, you could ask two questions. One is, if we increase the load and keep resources the same, how much our system degrades? Or if we increase the load, how much resources we have to increase to ensure no degradation or no change in performance? And then the performance itself, if it is an online system, so the response time is what is being used. And that's the time between the client sending a request and receiving a response. Now, every time you send a request and receive a response, it might be slightly different. So it's not a single number. The response times are a distribution. And when we are describing distributions with the number, we use percentiles. So, for example, if the 95th percentile response time is 1.5 seconds, that means 95 out of 100 requests take less than 1.5 seconds. So normally the response times are measured in P99, which is the 99th percentile, or P99.9, which is the 99.9 percentile. So in 1,000 requests, you will have 999 having a latency less than 1.5 seconds. These higher percentiles of response times are also known as tail latencies. And the idea is to really reduce the tail latencies. One caveat or sort of thing to keep in mind is head of line blocking, which means if it takes only a few requests to slow down to make all the subsequent requests slower or having more larger response times. So that's for online systems. For batch processing, throughput is the metric that we measure generally for performance, and it's the number of records we can process per second. Now, there is no one general approach for coping with the load. As the load increases, you could scale up, basically increase the resources on a single machine, or scale out, use more machines. Elastic systems can do this automatically, so they add computing resources when they detect a load increase and reduce the computing resources as they detect a load decrease. But again, there is no one single sort of answer, because the problem may be the volume of reads, writes, or the volume of data to store, or the complexity of data, or the response time requirements, or the access patterns, or some combination of these. And this book basically gives you the vocabulary and the insights into different aspects of these systems, which will help you to make these, decide on these trade-offs. So as I mentioned, no two systems are the same. So two systems with the same throughput may look very different. So consider this system that is designed to handle 100K requests per second, each 1 kilobyte in size. And another system which has the same throughput, but it's designed to handle 3 requests per minute, each with 2 GB in size. So throughput is the same, but you would require very different designs in each of these systems. And finally, we come to maintainability, which is about maintaining the software or the system that you build. So the majority of the cost of software is not in its initial development, but in its ongoing maintenance. And 3 design principles need to be kept in mind when designing systems for maintainability, which is operability, making it easier for operations teams to keep the system running smoothly, simplicity, which is making it easy for engineers to understand the system, and evolvability, making it easy for the engineers to make changes. So in summary, we discussed reliability, which means making systems work correctly even when faults occur. Scalability, having strategies for keeping performance good even when load increases. We discussed what load would mean in your system and what is performance and how to describe performance. And finally, we discussed maintainability, which is about making life better for engineering teams that need to work with the system. Thank you.